Welcome back to our channel. Today we are going to explore one of the most elegant and probabilistic data structure in computer science. Have you ever wondered how Chrome can warn you about visiting a malicious website almost instantly, or however Medium determines if an article title might be a duplicate? These all likely use Bloom filters behind the scenes. By the end of video, you'll understand what a Bloom filter is and why it's useful, the maths behind it, and also its application and limitation. So let's get started. Let us first see how the Bloom filter structure looks like. At its core, a Bloom filter consists of a bit array of m bits, all are initially set to 0. Then we have k different hash functions that map an element to one of the m positions in the array. So this is how a Bloom filter structure would look like, and now let's see how we actually add the elements into a Bloom filter. Adding the element into a Bloom filter is actually the most important part. Now let's discuss how we actually add the elements. So now we have discussed the structure about the Bloom filter. We have a m bit array, and k different hash functions. Now let's suppose we need to insert a word apple into a Bloom filter. So how we'll do? We pass this apple through all the k different hash functions. Let's suppose k1 will pass an apple. It would give me a bit of 1, let's suppose. Then we pass it to k2 and it give me a bit of 6, and then let's suppose we have k3 and it gives me a bit of 9. So then in the Bloom filter, which was initially set to 0, we'll set these bits 1, 6 and 9th bit to be as the set bits over there, and rest all the bits remain the same. So this is how the addition is actually performed in the Bloom filter insertion. But how do we are checking if actually the element that we have inserted in the Bloom filter is actually existing there or not? Like if we asked a query, check whether an element is there or not. So let's move on to how we are actually checking. So we are given an m bit array, and we know that we have inserted a word apple at positions 1, 6 and 9. Okay. Now let's suppose I have been asked a word orange or an apple again to check if there exists or not, and we have 3 hash functions as we have done. So we have these three hash functions. So we'll again pass this word apple to these 3 hash functions, h1 apple, h2 apple and h3 apple. So then this will gives me some bits a, b and c, and then we'll check for these all the abc bits whether these all are set or not. So if they all are set, then we say that it might be that apple is there in the set. There is a probability that apple is there in the set. But if at anyhow any of the bits is 0, then we for sure that say that apple is not there in the set, because while the time of setting apple in the set, we assure that all the bits that given by the hash function are set to 1. So if that apple is being set in the Bloom filter or being present in a set, then that particular bits would have been set to 1. So if we get a 0 for anyone, for any of that bits, like at the position where the b is present is a 0, then for sure we can say that it would be a no. So here is the answer to the question of what we are just looking upon, how the Bloom filter tells us whether it is a yes or a no. Now what if I inserted apple in the set, and let's suppose it gives me the bits 1, 6 and 9, and then I have inserted orange, that gives me the bit 1, 7 and 8, and 1 is already set and 6, 7 are the new bits that are being set. Now let's suppose I have to check for banana. Let's suppose when I have hashed this word banana for all the 3 hash functions, it would give me, let's suppose it gives me 6, 9 and 8. It could be anything that we could do. So it would give me all the 1, 1 and 1, and check if these 1, 1, 1s are there in the set, and it could give me a yes for that. Like yes, it might be present, but we know that banana is not there in the set because we have not inserted banana over there. So this is how the false case for Bloom filters come into picture. Like the yes for a Bloom filter is just a probability. It just gives us the probability that it might be there and might not be. Now here is the maths behind the Bloom filters. The probability of a false positive depends upon size of the bit array, number of elements in the set, and number of hash functions. The formula for the optimal hash functions would be m by n ln2, and also for the probability of false positive would be it would be 1 minus e to the power minus kn by m all to the power k. Moving on to the application of the Bloom filters. Bloom filters are incredibly useful in scenarios where memory is limited, false positives are acceptable, and false negatives must be avoided. So the real life examples are web browsers, database systems, CDNs, spell checkers, network routers, streaming services. Bloom filters are brilliant examples of space-time trade-off in computer science. By accepting a small probability of error, we gain tremendous space efficiency. Next time you see a spell checker, browse the web, or stream music, remember the Bloom filters might be quietly working behind the scene, saving memory and keeping things running smoothly. Thanks for watching. If you have any questions about Bloom filters or want to see more videos on probabilistic data structures, let me know in the comments below. And please like, share, and subscribe. Thank you.